Okay, time to focus on me.
This is intense, though.
Tyson's right.
It's a battle of time.
All right, lesson 5-1B. Ready to go over the warm-up?
Sure.
Okay, this is good review over what we talked about in lesson 5-1A. It says, if line MP, I'm going to highlight that in green. If line MP is a perpendicular bisector to line segment LN, so that means two things. It means it's perpendicular, Siler. It means it's perpendicular, and it means it bisects it, which means it crosses at what point, Siler? Which is the midpoint. So probably the easiest variable to find first here would have been y, because you know it bisects it. So you just would set up that PL distance has to be the same as 16. You should have gotten y to be 7 for that first one. Okay, here was the second kind of piece of the perpendicular bisector theorem. Any point on your perpendicular bisector, so if I'm looking at M, that's a point on the perpendicular bisector, is equidistant from the end points of the segment. So these distances right here are the same. It's equidistant. Okay, we talked about that no matter where the point is. So to solve for x, you should have set those two equal to each other. And you should have x to be 4. Okay, so then plug those back in to find mn and lm, and obviously we know we should get the same number. I got 37 for both of those. Okay, do we do okay on that? Know what a perpendicular bisector is? All right. The next one was a little vocab with the other part we talked about, angle bisectors. So here it tells me that BD, line BD, bisects angle ABC. Now my angle kind of has like end points here, so this one is a little different. But if it's an angle bisector, it means it splits this angle right into two congruent angles, or right in half. So to find x, I know that that second angle right there, that 5x minus 6, also has to be 64 degrees. It splits it right in half. So I solve for x first this time. I got x to be 14. That's a 7. Okay, now the angle bisector theorem is at any point on the angle bisector, as long as we're talking about the perpendicular, the shortest distance, is equidistant from the sides of the angle. But they kind of just showed you the end points of the angle here. So they didn't necessarily like say that was perpendicular per se, but they are showing you like to the same 2 points, the same end points of the angle. So these are indeed equidistant. All right, so you should have set those equal to each other to solve for y. I got y to be 10. And then to find AD and CD, plug that back in. I got those both to be 19. Okay, any questions with that so far? We got that down because we all did our homework and practiced, right?
C.
All right, so this is the second half of lesson 5-1, and we split it into two because these are really, really important. So first we need to focus on like what a perpendicular bisector and angle bisector are in triangles. And today we're gonna like build off of that. We basically have like two big vocab words of the day, and this is actually the last lesson of 2021.
Hurrah!
Isn't that crazy?
That is great.
We go on to another lesson until you come back from Christmas.
Make it want to leave next.
Wow.
Next crazy.
I'm so happy to end my year with you all. Alrighty, folks. Here's a couple vocab words for you. Concurrent lines, which could technically be a line, right, or a segment. Concurrent means that they intersect at the same point. So I drew 3 lines up here for you. Well, actually, this one's a ray. But do you see how they have that common point where they all intersect?
Yeah.
That's called my point of concurrency. The point where they intersect. Okay, now we have special names for these points of intersection depending on what characteristics of the triangle we're looking at. So the first one we're going to do are the perpendicular bisectors. All right, this diagram might look confusing to you, but I mean, it's nice that mine's color coordinated. It's not too bad once you look at the sides are in blue. So A, B, C. There's my triangle they're talking about. I'll explain kind of like the circle and all these markings in a second. And then all the gray ones, which I'm going to trace in green. If I'm looking at side AC here, it's showing me 2 things. It's showing me it's perpendicular. What else is it showing me? It bisects, meaning that green segment would be what? Not just the bisector. The perpendicular bisector of side AC. Okay? All right, this one right here, if I'm looking at side AB, perpendicular bisector, there'd be your perpendicular bisector for segment AB. And then they're just kind of showing you that these are really just lines. They could go on forever. All right, then my last side here, BC, see this one? Perpendicular bisector. So, your perpendicular bisectors, this will always work in a triangle, will intersect at one common point. We call it a point of concurrency. Point of concurrency. And we have a special name for it, for where the 3 perpendicular bisectors intersect. It's called the circumcenter. So go ahead and label that. On your picture. I did mine in orange. Circumcenter. And you need to know, hey, that means that's where the 3 perpendicular bisectors intersect. So this right here, the green ones, those are all perpendicular bisectors. I can shorten this. Let's do this. You can write it out if you want to, but and then maybe also just show that technically it's intersecting, because this will come into play later, because it's a bisector at the midpoint of each side. Oh, thanks. It's knocked me over. Yes.
Is it a circumcenter because there are 3 perpendicular bisectors?
There's always going to be 3 perpendicular bisectors in a triangle.
Okay.
Because we're doing one of each side.
Yeah, that makes sense.
Yeah, good question. Now, this one, it takes place like inside of the triangle, right?
Yeah.
And that depends on what type of triangle we have. Here it's showing you, like, if you're to put all the vertices like on a circle, that this triangle ends up being like inscribed. That means like inside of the circle. That's just gonna kind of help us with one of our theorems. But here's like our 3 possible locations of the circumcenter. What I was talking about before. It depends on what type of triangle it is. All right. If we have an acute triangle, that was one we were just looking at. I'm classifying this by its angles. If I have an acute triangle, the circumcenter, which they're calling point P, will be located in like the interior or inside the triangle. Like that, inside of it somewhere. If it's an acute triangle. If it's an obtuse triangle, you can see in my second picture there, I have like an obtuse angle. These are all perpendicular bisectors. If you wanted to, it's a little hard to visualize on this picture. I had a hard time finding a nice picture that I liked. But going back to this one, like here, they're showing you like that would be the perpendicular bisector of that side. This one would be here. This one would be here. So that's where the three perpendicular bisectors of each side are intersecting. So this one, like here's a perpendicular bisector. Here's the long side perpendicular bisector. Here's this one. So where those three intersect actually takes place outside the circle. That can happen, or not circle, sorry. Outside the triangle. On the exterior would be like another way you could phrase that. And then if we have a right triangle, here you can see I have this perpendicular bisector, this one, and then this one right here. That point of intersection, that circumcenter ends up being right on the hypotenuse. And that will happen for every right triangle. Okay, so just keep in mind it might not always necessarily be inside the circle. We'll look at some examples. You'll get to do some on your homework. All that good stuff. Okay, now here's where the circle piece of this picture is going to kind of come into play to help us with this theorem. So now that we know what a circumcenter is, here is the circumcenter theorem. The perpendicular bisectors of a triangle intersect at a point called the circumcenter, as we just talked about. It's equidistant, which means the same distance, from the vertices of the triangle. So in my picture, and again, I know yours aren't color coordinated, but if you have colored pencils or pens or something, they're showing you in red here. In red, these are all the perpendicular bisectors. See how all those lines are drawn to each side? They're showing you they're 90 degrees, so they're showing you they're perpendicular, and they're showing you that it bisects. Okay, that's what the red is showing you. So here, point P, where those three perpendiculars bisectors intersect, that's my circumcenter. Here's the theorem. Let's go back to this for a second. If I were to, let me use purple. If I were to take this distance, so if I were to like inscribe this in a circle, this is the center of my circle. To each vertice, those are all, what do we call that in a circle, the distance from the center to the outside? The radius. So this would be a radius from A to C. I don't know what I call this C. Let's call it P. From A to P, from P to B, from P to C. Those would all be different radius. Plural of radius is radii. Those would all be different radii of a circle. So those are all going to be the same distance. That's what this theorem is saying, that these are all going to be the same distance. I'm going to do a little squiggly line here because I already used all the hash marks. So PA, this distance from the circumcenter to the vertice A is going to be the same as PB. The circumcenter to that vertice is going to be the same as PC. From the circumcenter to that vertice. Okay. Oofta, that's a lot of markings on there. So let's try a couple examples. Starting with this one. This one says, find BG, which means like the length of segment BG, if G is the circumcenter of triangle ABC. Okay, so they're telling me this indeed, this point, G is a circumcenter. The line segments drawn to each side would be your perpendicular bisectors, because that's what a circumcenter is. It's where those intersect. What they're showing you in red are the distances from the circumcenter to each vertice of your triangle. Okay, so that's what they're showing you in red. Again, I know yours isn't color coordinated, but if I want to find BG, I know, according to that theorem we just talked about, that distance is the same as all the distances from each vertice to the circumcenter. Those are all equidistant. That's what that theorem says. So BG is going to be the same as AG, which is going to be the same as CG. Now, in this case, they tell us AG is 9, so BG is also going to be 9. Equidistance. And again, you can think of this if you're to like draw a circle. Those are all just radii at least this circle. Okay. Are you done, Evan?
Yeah.
Okay, you can sit it on my desk chair and then I won't miss it. All right, the next one says find AD if, again, G is the circumcenter. So AD, they're talking about this distance right here. All right, now here's where I need to know what the vocab of a circumcenter means. It's a perpendicular bisector of that side, meaning it splits that in half. Meaning AD is going to be the same distance as DB. So it'd just be 6 units. Okay, not bad, right? This would be hard to do if you didn't know all those characteristics of the circumcenter. I don't really think of it as theorem. I more think of it as just like characteristics or properties of a circumcenter. Last one. Find the measure of angle. This is still going with this picture. GFA. What would the measure of that angle be?
9.
Why?
Perpendicular.
Exactly. It's perpendicular bisector. Now I marked it on that side, but I could have done this as well. We know it's a perpendicular bisector. That's what a circumcenter is. So that's obviously going to be 90 degrees. Okay, let's try one with algebra. A little bit harder. This next one says, find PZ if P is the circumcenter of a triangle XYZ. Okay, so again, I see that word circumcenter. I'm like, hey, that means it's where all the perpendicular bisectors intersect. And they're showing you that in blue this time. They're showing you it in blue. Well, mine's on blue. Now, if you're wondering, you're like, what the? I only see 2 perpendicular bisectors. This is not a perpendicular bisector. This is showing you the distance from the circumcenter to the vertice Y. If I were to draw the perpendicular bisector, I'm going to try to do this the best I can. Where it goes through that point and it's perpendicular, something like that. They're just showing you that's where all 3 of these intersect. Would be that point P. And we know it's on the hypotenuse because it's a right triangle. That will always hold true. All right, so that's what they're showing you. All right, so what that means is that it splits all of these in half. So here, when they tell me that px is 3x plus 2, I mean, you can label this 3x plus 2 if you want, but we know it like splits it in half. All right, here's what else I know. This is a fun problem. Py, which is not a perpendicular bisector, it's a distance from the circumcenter to the vertice, in this case y. That distance is 4x minus 8. All right, now since this is right on the hypotenuse, these lengths kind of double in how they're represented. They're bisected. That's like one way you could see it. But this is also a distance from point P to the vertice Z, right? And this distance is from point P to the vertice X. So these are all, I'll double hash these. These are all equal distance as well. All right, so yes, point P is a part of the perpendicular bisector. It's also one of these in purple. It's also a distance from the circumcenter to the vertice. So this is also 4x minus 8. So to solve for x, we can set those equal to each other, because we're talking about the same distance. And then we'll have to actually find what PZ is. Okay, so move over the 3x, add over the 8. We get x to be 10. That's not what they asked me to find. They want me to find this distance. So there's two ways you could find this. You could either plug it into the fact that we know it bisects, or plug it in that it's equidistance from the circumcenter to the vertices. I did this one. Either way, you'll get 32. Okay, does that make sense? I feel like some of you guys look confused. Or why those are the same. Okay, next one. These ones are fun. Normally when you see this, you get all worried that you have to do distance formula, right? Guess what? Not today.
Wow.
Woo-hoo. It says find the coordinates of the circumcenter where all the perpendicular bisectors intersect. I'll say that over and over and over until you can't stop thinking about it. Of the triangle with these vertices, A, B, and C. Let's go ahead. Let's just plot them as we go here. A is -2, -2. B is -2, 4. C is 6, 4. If you have a straight edge, use it. Take your triangle. What kind of triangle does this look like? It does look like a right triangle. So already, I'm thinking my circumcenter is probably on the hypotenuse. So many passing of materials today. I'm so confused. Okay. So, what we're gonna do, exciting, we're gonna find and draw in the perpendicular bisectors on each side. So you know two things about the perpendicular bisector. We know they're perpendicular, and we know it bisects at what point? The midpoint. So we're gonna start by finding the midpoint of each line segment. Now, folks, when you have vertical and horizontal lines, I'm okay with you using some logic here. Instead of using the midpoint formula, you can count this segment. It's 6 units long. So obviously the midpoint's going to be right halfway between there. If you need to use the midpoint formula, you know how to do that. If I'm doing AB, add the x coordinates, average them halfway, add the y coordinates, average them halfway. But we see the midpoint there is at -2, 1. Okay, everybody with me? -2, 1. I'm going to do that one in green. Another easy midpoint one would be BC. All right, without doing the formula, can anybody figure out what the midpoint would be there? Count the segment. It's 8, so halfway would be 4. Exactly, that order pairs 2, 4. Again, if you must do the midpoint formula, you can do that. Whatever makes more sense to you. Either way, you get 2, 4. All right, now with the slanted segments, you have to use the midpoint formula. You may be able to figure out logically again what it is, but unless you use a straight edge, it's hard to tell exactly. So please actually use the midpoint formula for the slanted ones. All right, so you got AC here, so -2 plus 6 over 2, -2 plus 4 over 2. So much practice with midpoint formula. Here I get 4 over 2, which is 2. Here I get 2 over 2, which is 1. 2, 1. All right. So what we're going to do next, now we know that's like where all the perpendicular bisectors are going to intersect on each segment, on each side. What we're going to do next is determine what would be perpendicular to each side. So we're going to have to find the slope of each side. Now again, with some vertical and horizontal lines, so let's go to AB again first. Now I'm doing lowercase m, which means slope. What's the slope of vertical lines? This is 0. Horizontal line 0. Vertical. Undefined. Good. Again, I'm okay with you just telling me, hey, that's undefined, Miss Hentridge. I know what a slope of vertical line is. That's great. If you need to do slope formula, change in y, 4 minus -2, over change in x, you'll see you end up getting 6 over 0, and we need to know, and define, can't divide by 0. Okay, we'll come back to this. Let's just keep finding the slopes of each segment. So BC, horizontal line, 0, exactly. Again, if you got caught up in the moment and you were just doing your formulas, you'll still get this. Hey, 0 over 8 is 0. 0 divided by 8 is 0. All right, with the slanted line, you could count rise over run if you wanted to, or you can do the slope formula. But if you know you get from point A to C, you can also just do your rise over run. That'd be up 6 over 8. I'm not going to do the formula again. 6 over 8, which is 3 over 4. Positive. Up 6 over 8. So reduce that 3 over 4, which makes sense. That'd get me to the midpoint. Right? Up 3 over 4, up 3 over 4. Okay, now the fun part. So now we're going to draw in the perpendicular bisectors with all the perpendicular slopes to each segment. Okay, here's kind of a tricky one though. If I have an undefined slope, what would the slope of the perpendicular line be? Tyson?
0.
0, right? Think of a vertical line. A line perpendicular to it would be horizontal, right? Or take the reciprocal right here. Reciprocal of 0 over 6 would be 0. All right, so we need to draw a horizontal line. There's my perpendicular bisector of AB. Horizontal line. You're going to want to use a straight edge on your homework. If you don't have one at this moment, it's okay. But especially ones that aren't right triangles, you're going to want to use a straight edge. Okay, BC. If this line has a slope of 0, what is the perpendicular line going to have a slope of? Undefined. It's going to be vertical. Or again, take your math right here. Do the reciprocal. 8 over 0. Undefined. So this one's going to be vertical. Again, that makes sense. That looks like it would be perpendicular to that side. All right, then I kind of have my weird one. AC is 3/4. So opposite, reciprocal, negative 4 over 3. All right, so what you're going to do, I'm not going to make you find the whole equation of this line. We already did that. What you're going to do is just start here at your midpoint, and you're going to go down 4. 1, 2, 3, 4. To the right, 1, 2, 3. And I just quick take a step back and I look. I'm like, yep, that would give me a negative sloping line. So then take your straight edge. There's your perpendicular bisector of that edge. Okay, so that's how you would do it if it's not vertical or not horizontal. I actually think those end up being easier to find the slope. Now, if you use a straight edge and you find the midpoints are correctly, you should get a point where they all intersect. And mine ends up being right here. It's kind of not the greatest because I use a straight edge. But it should be right there on the hypotenuse, which makes sense because that's a right triangle. So my circumcenter, which is where the 3 perpendicular bisectors intersect, would be at that point. It looks like 2, 1. Now, you might not always get an exact point. Like, it might be like a decimal that you have to approximate, and that's okay. Just try your best. I promise if you use a straight edge, the more accurate it's going to be. Okay? There's a few on your homework like that aren't right triangles that you have to do the perpendicular bisector for each side. I like those ones. That was fun. All right, that was one big vocab for today. Here's the second big vocab word. We probably won't finish all these notes. We didn't finish them in 7th hour, but that's okay. Here's the second vocab word. Important. If I take all the angle bisectors of a triangle, so I'm going to do these in green. A is an angle bisector, meaning it splits angle A in half. B is an angle bisector, splits angle B in half. Say C is also an angle bisector, splits that one in half. They will cross at a point of concurrency, aka where they all intersect, and this is called the incenter. It's where the 3 angle bisectors intersect. So in this case, this is the incenter. And all my green ones are angle bisectors this time. Oh, green. Angle bisector. Okay, now this time drawing a circle inside a triangle helps us see this next theorem. So the angle bisectors of a triangle intersect at a point called the incenter, and it's equidistant from the sides of the triangle. All right, so if I look at this little circle, and if I see where it touches the outside of my circle on each side, these all end up being the shortest distance. And if you see, those are all example of radii in the circle, right? So they're all going to be equidistant. That's what this theorem says. So this picture is showing you, I'll highlight them in green. Angle bisector, angle bisector, angle bisector. Now careful here, these aren't showing you the perpendicular bisectors. That's not what they're showing you here. They're just saying the distance, the shortest distance, which ends up being the perpendicular distance, those are all going to be equidistance. As long as we have an in-center intersection of the angle bisector. So in this case, PA, if P is the intercenter, or sorry, not PA, PD is going to be the same as PE. This is going to be the same as PF. Here's one note I want you to make in your notes. The in-center, and this is easy to remember because in-center, this one is always located in the interior or inside of the triangle. I can't draw an angle bisector that has a common point of intersection like outside of this. So the in-center should be always inside. Okay, we'll just try a couple. We'll see what we got for time. We got about 5 minutes left. Again, this is not a perpendicular bisector. You can clearly see like that doesn't bisect BC. It's different. So this one says, find ST if S is the in-center of triangle MNP. In-center meaning intersection of all the angle bisectors. So these lines drawn from the angles, that's drawn in right now, those are bisecting those angles. That's all the information I know from them just telling me it's the in-center. Okay, so they want me to find ST. They want to find this shortest distance from the in-center to the side T. Now I can see that they drew in the distances to each side, and based on what we just talked about, I know those are all equidistant. So I know ST is going to be the same distance as SU and the same as SR. However, I don't know what any of those are. They don't label any of those. But I want you to zero in on this little triangle right here. I'm going to highlight it. Because you can see, hey, and if I were to blow up that triangle, it would look like this. Let's see, this would be S, P, U. We know this is, there's my tick mark, and we know U to P is 8, and we know S to P is 10. Okay, if I were to blow it up, it'd look like that. I have a right triangle here. Any ideas of how I could find that distance? Ooh, Jessa. Python! Nice. I'm going to call it X. You can call it whatever you want. But my 2 legs squared equal my hypotenuse squared. All right, let's quickly solve this. That's 64. That's 100. Subtract, we get 36. Square root both sides. That gives us 6. These are all distances of 6 then. So we know ST is also going to be 6 units, talking about technically the in-center theorem. Again, I like to think about it just a characteristic of the in-center, that it's always equidistant from each side. Again, it's not showing us a perpendicular bisector. All right, last one. Let's finish this up, and then we'll call it a day. Find the measure of angle SPU. And we're looking here, we're like, they don't show me either of those angles. But I do know that this angle is 31, so this angle is also going to be what, folks? 31. It's an angle bisector. So I'm going to have two angles of 31 degrees, or I can think of that as 62 degrees. In this angle right here, they're showing me this one's 28. So this angle is also going to be 28, or a total of 56, however you want to think of that. So I'm going to call this angle Y. So I know I have two of those Y's, and since they're all in that big triangle, they have to total how many degrees? 180, triangle angle sum theorem. Okay, so I'm going to solve this quickly because we're running low on time. I got Y to be 31. So the measure of angle SPU would be 31 degrees. And again, folks, you could subtract off, the 62 and the 56. We're left with 62 degrees for this whole angle, and they just wanted that half of it. So we divided it by 2 to get 31. Okay. I do want to pass out a worksheet.